Um, Hi, I'm William Gurecky. I work at Oak Ridge National Laboratory as a nuclear engineer. I'm also working with my colleague Constantine, and today I'll be presenting on exponential time integration schemes for stiff systems implemented in Rust. So I'll get right into it. We recently published a package called ORMATEX. This stands for the Oak Ridge Matrix Exponential Toolkit. It is a mixed package implemented both in Rust and some prototyping in JAX and Python. Currently, the Rust implementations of the exponential integrators are active work in progress, and we're adding higher order exponential integrators kind of as we speak. It's active work. So what does ORMATEX do at a very high level? Well, it provides some niche capabilities that we weren't able to find in the Rust programming language when we started this project. And that is, it provides matrix exponential capability. This is like XPIM from, say, MATLAB or SciPy, right? It also provides related functionality for the phi-functions as well as phi-vector products, which are very important when you construct exponential integrators. And ORMATEX also implements several classes of exponential integrators, which I will cover at least a few of them in this talk. So why might one be interested in ORMATEX or interested in exponential integrators in general? They are applicable, particularly applicable to stiff linear dominant systems, and they are competitive with implicit integrators in those circumstances. Um, so we are utilizing FAIR, their linear algebra crate that I have noted here at the bottom of this slide, for all of our sparse and dense matrix operations currently. We would like to support other linear algebra libraries in the future, but currently everything as far as storage and matrix operations is all FAIR-based. And we provide a Python interface that is also a work in progress to all of our Rust-based exponential integrators via Py-O3, which allows you to utilize these exponential integrators from Python if you're not too familiar with Rust. It also allows you to express the dynamics, or the right-hand side of your PDE or coupled system of ODEs in Rust or JAX, but then also leverage the Rust integrators for the time stepping. So a high-level overview for exponential integration, how it works. This is only a very high-level review. But the idea is that you split a system of ODEs into a linear component and a remainder nonlinear component. And then if you multiply each side of this equation with an integrating factor and you integrate both sides of the equation, you wind up with this second equation, which is exact as written, but it does not specify how you estimate this integral. Taking the simplest possible estimation of this integral using a box rule yields the simplest exponential integrator called exponential Euler, essentially. And what's interesting about this integrator is that if your linear term here dictates the stiffness of the problem, meaning the entries of this L matrix, I want to be clear, L is a matrix here, coupling multiple ordinary differential equations in this case. If that contains terms which vary in magnitude, meaning that it's very, very stiff, these classes of integrators can be very profitable because you can calculate this matrix exponential with extremely high accuracy. So this is the type of problem that you would be interested in solving with an exponential integrator. And I want to be clear, they are applicable to linear and nonlinear problems. It's just particularly advantageous if they are linear dominant, and that's where the stiffness is coming from. I'll say a few words about how this fits in with explicit and implicit integrators. So explicit integrators are very scalable. They are quite easily parallelized, but they suffer from a time step restriction. So this is particularly for stiff problems. So this would lead you to the implicit class of integrators. But in certain circumstances with large time step sizes, implicit integrators, while stable for large time steps, can introduce numerical dissipation and numerical dispersion. And these exponential class of integrators do not suffer from the same level of dispersion as implicit integrators do. And they also allow you to take large time steps even if your system is stiff. So they can be quite advantageous in this way. But the downside is that these exponential integrators can be somewhat hard to scale to very, very large systems and parallel computers. So what does ORMATEX currently implement? We have on the top, the top are basically foundational capabilities. So we have a matrix exponential capability. We have phi-functions for both dense and sparse matrices. We also provide Krylov-based phi-function evaluations, which allows you to construct essentially matrix-free type exponential integrators. So this is implemented using Fair's linop trait. So far in the Rust side, we have three exponential integration routines. We have exponential Euler or exponential Rosenbrock order 2. And we have a third order exponential Rosenbrock scheme. These are both Krylov backed. So again, these can be applied when you don't necessarily have to form the matrix A. All you need is the linear operator A. We also have these exponential propagative iterative methods as well, which I have noted down here as the reference for those papers. And these are interesting because it allows you to save calls to Arnoldi, which is one of the bottlenecks in these methods. Is essentially you have to call Arnoldi, and this chi-ops routine allows you to save several calls to an Arnoldi routine. We are also working on a polynomial interpolation technique based on layer points for these matrix exponential evaluations, which leads to a different class of exponential integrators, which is quite attractive. These are basically an alternative to Krylov-based exponential integrators. So those are in progress currently. So how does this, at a high level, how does this crate get used? So this just has a super easy example. This is a purely linear problem. This is how you would evaluate the matrix exponential using our crate. We implement several different ways to do this, but one is a Padé approximation, quite simple, and the other is a partial fraction decomposition-based method, which we provide several of. This is essentially a contour integral approach on the complex plane, and you're able to really get very high order accuracy of this matrix exponential with these routines, but they are very easy to use. That's kind of the highlight here. For this simple system, of course, if this is a purely linear system, we can actually evaluate the dynamics by just taking the simple for loop and evaluating the matrix exponential and applying it to the right-hand side vector. So that's just the system in the bottom of your screen. Going into a bit more detail, we have visualizations of the system. So we're basically looking at the difference between an exponential integrator on the left-hand side of the screen and an implicit integration scheme, in this case, an explicit singly diagonally implicit order 3 scheme. The order is not important here because this is a purely linear system, but again, this is a contrast between the exponential integration schemes and an implicit integrator. If we take a higher time step size, which is what is shown in these two figures, you start to see that the implicit integrator starts to essentially drift away or lose accuracy as you step forward in time. And it in fact does not recover. You just drift further and further away from the true solution if you take larger and larger time steps for this particular linear system of equations. So this is again a system of ordinary differential equations where L is a matrix and U is is a vector. So now kind of summarizing those results, we have all the exponential integrators that we have implemented show up here at the bottom of this plot, which is showing that you achieve nearly machine precision for, since this is a linear problem, we expect this, you achieve very good accuracy for this problem at any time step size. Whereas the implicit, here you have implicit Euler, and then you have ES-Dirk order 3 and 4 at the top of your screen, showing that it takes quite some time to achieve good accuracy for this class of problem. Moving to a slightly more advanced example, we have not only this linear term now, but we also have an advection term that is advecting all of our species, in this case, across the screen from left to right. And this visualization is done after one single cycle of this bump being advected across the domain. So this is using, all of these plots are using an implicit ES-Dirk scheme. And moving from left to right, we start with a small time step size with a CFL number of just greater than 1, all the way up to a CFL number of greater than 12. So that's what's happening from left to right, is you're getting an increase in time step size. And we start to see that we get numerical dispersion from this implicit integrator start to creep into the solution. So while this is stable, you suffer significant accuracy loss at high time step sizes for this transient problem. Moving to the exponential class of integrators, again, because this is actually just a linear problem, and I will say a few words on the spatial discretization scheme. This is a finite element scheme. It's using a Gauss-Lobato quadrature, so some simple spectral elements in 1D. This is to get a diagonal mass matrix, but in any case, this is a purely linear system. So again, we recover extremely good accuracy from all of our exponential integration schemes, which you can see again in this plot. All the exponential integrators are, the exponential Rosenbrock integrators are essentially hitting the spatial discretization error at any time step size for this problem that we just showed on the previous slide. And again, the implicit integration schemes are up here at the top of this plot. This is an interesting figure because it also shows that these guys do not reach an asymptotic convergence behavior unless you take very small time step sizes. So here you kind of see an elbow in the plot. That's kind of why this happens at high time step sizes. This plot also shows that exponential integration schemes, essentially these partial fraction decomposition schemes, are essentially very closely related to Crank-Nicolson. In fact, this exponential integrator partial fraction decomposition order 2 method is very similar, and you can see it behaving very similar to Crank-Nicolson here. So with that, I'll go ahead and conclude. Again, you can access our matrix or our exponential integration package here. It is currently a work in progress. There is a lot of opportunity to, particularly on computing Jacobian vector products here, where we're kind of looking forward to leveraging any sort of autograd implementations that might come about in the Rust community, because those fit very nicely to time integration packages in general. But they are very Jacobian vector products are a key component of implementing exponential integrators. So we're hoping that we can collaborate there. So that's the end of my talk.
Well, thank you, William. You do have two questions here. The first one is, do you already have buy-in from management to implement this in Rust instead of the typical C, C++ Fortran? How do you or your team justify it and pitch it to them?
This is a good question. So this is actually the way that this was justified to our management or team is that this is a prototype implementation of these exponential integration schemes that we are currently implementing. We are also pursuing an implementation in C++.
Okay. Do you?
But this is a prototype package, to be clear. Yes.
Okay. And second person asks, are there any exact solutions for these problems? Bateman, advection, slide 11.
Yes, and while I have not shown them here, the exact solution, this slide was generated. This true value is the exact solution. So yes, we have an analytic solution for this problem, and indeed we have an analytic solution for this problem as well. Obviously, there's no issue in calculating an analytic solution for this either, and that is also how this slide was generated. This is compared against the analytic solution. So that is a good question, and yes, we have an analytic solution for both of the examples shown here. Yes.